All right, so for the third part of lecture 1, let's discuss the most widely used method to implement logic gates. Of modern times, this is the CMOS logic gates. No? So, we'll cover MOS transistor switches and then the NMOS inverter, and then we'll transition over to CMOS, no? Which is neither NMOS nor PMOS, it's a CMOS. So, first off, let's replace the BJT that we used for an inverter earlier with an NMOS version. Okay? So, what happens with an NMOS? Well, NMOS has three operating states, right? We have the cutoff, we have saturation, and we have the linear mode. No? So, when VGS is greater than VTH and is less than VGS minus VTH, no? Then the MOS is considered to be in the ohmic mode. That is, no? This is known by many names. This is also known as the triode region. This is also known as the linear region, no? But in this region, the important thing is it is kind of the analogy to the BJT's saturation region. Now, the behavior that we like from the NMOS here is that the channel is essentially equivalent to a resistor here. No? More precisely, it's actually a function of VDS squared instead of VDS, which would be the resistor, but it's close enough. No? So, a smaller resistance can be achieved by increasing the VGS. Now, for us, if we want to use it as a switch, if the load resistor above, no, the NMOS is much greater than the RDS on of the NMOS, then this is good enough for the purposes of a switch. No? So, shown here, if we increase VG to above VTH, no, and decrease this such that it will turn into the triode region, then we get a voltage divider here. And if RDS on is much less than RL, then this is basically what? This is basically this circuit. No? If RDS on is much less than RL. Okay? Now, same thing happens with the PMOS transistor switch. It's just that the applied voltages are opposite in polarity. For here, we need to pull down VG such that this voltage goes above VTH to create the inversion layer, no? And then make sure that this voltage goes up so that we squeeze the voltage overhead of the transistor to put it in the ohmic region. So then when it's ohmic, we have an RDS on in series with an RL. And again, if the RL is much greater than RDS on, this is essentially a short circuit. No? Now, one thing that is introduced really is for most practical purposes, if you're trying to breadboard something, and which one do we want to use? Is it a PMOS or an NMOS if I'm allowed to use both? Well, typically we want to use an NMOS. Why? Because electrons have a higher mobility for the same size of device, for the same general architecture, no? The NMOS will have an RDS on that is smaller. And we want it to be smaller so that it doesn't affect the behavior of the circuit significantly, since we're just using it as a switch, right? So, let's use the NMOS with an inverter, just like we did for the BJT. No? So, okay. So, we use it as an inverter. So, we find that, all right, it starts off in cutoff, then it goes into the active mode after VTH. Then, after some time, this goes to the triode region. No? Which makes sense, right? This is what we expect from a an NMOS or a common source rather. No, this is a common source amplifier. We just use it in triode region. That's why it's an inverter. No, so this is something that makes sense. So now, what do we consider logic 1 and logic 0 here? Well, when does it start going on to the -1 slope? It's somewhere around here. When this start going on to the -1 slope for the lower region, it's around here. No, so then we want to arbitrarily choose where to consider the input high or input low. In fact, for MOSFETs, we would like the input low actually to be VTH. And this obviously is so that when we put it into the next inverter, we are sure that the MOS of that inverter will be in cutoff. No? We choose VIH to be up here instead because of this reason. No? The input high must be such that when VGS is greater than this VIH, no, the VDS is less than VTH. No? So, why do we want to do that? It's so that when the output here, no, so for example, if the input is here above VIH, it corresponds to an output that is below VTH. No? And that's important so that when we throw the output to the next MOS, we have a VIH, no? At most, a VIH that, the VOH rather, or VRL, is less than VTH. So then it guarantees that the next inverter's MOS will be in cutoff as well. No? So this is how we choose the VIH and VIL for the NMOS inverter. Okay? So, introducing, finally, the most common logic family nowadays, it is the CMOS. No? So, the C here stands for complementary, meaning we use both the PMOS and the NMOS. Okay? So what happens in a CMOS? Let's say, for example, that we have this circuit and we put in a VDD as the input. What happens is that naka-on yung NMOS but the PMOS is not on. No? So, what happens? The NMOS is a small resistance, but the PMOS is a very large resistance, which means that the output is practically zero, right? Because we're shorting it to ground. On the other hand, if we have an input that is ground, the NMOS is open, but the PMOS is closed, practically closed. So then we're shorting the output to VDD, giving out a logic 1. Okay? And this is the operation of a CMOS inverter. So how do we analyze the operating regions in a CMOS inverter if there are two different transistors? Well, then we cordon off every single portion wherein there are different combinations of the operating regions. So for example, here, V out, if it's high, no, means that the NMOS is in cutoff, right? So that's the region A, right? The PMOS will be linear. Then, after a while, no, as you increase the V in, that NMOS will go into saturation because it's no longer in cutoff, it's above the threshold voltage, no? While the PMOS is still in linear. Now, as we increase the input voltage, the NMOS starts getting stronger and it starts pulling down the output voltage. After a while, it pulls down the output voltage enough such that the PMOS is no longer choked for voltage headroom. So then, if this output voltage is low enough, the PMOS has enough working space of voltage to go into saturation. Yes, to go into saturation. No? So this puts us into region C, both of them in saturation. No? Next, as the NMOS gets even stronger, it pulls the output voltage even lower. In fact, it can pull it so low that it loses its own headroom, thus transitioning into its own linear region. No? Then finally, as the NMOS gets even stronger, it pulls the output much lower such that the voltage, rather, as we increase the V in more, no, we eventually exceed the one that this the voltage level that is required by the PMOS to stay on. So then we turn off the PMOS and then it transitions into cutoff. Okay. So with that, here is the transient response of a CMOS inverter. So what happens? Typically, it's just the CL really that contributes significantly to the transient response of a CMOS inverter. So for example, here, no, we turn Vin up, no, at time equals 0. So if Vin goes up at time equals 0, then the PMOS is off and the NMOS is on. So it's equivalent to an R on, no? Now, since this is off, it has no resistance, rather it has infinite resistance. And since this is R on, it has a pretty low resistance. So then the overall behavior of the output would be such that the load capacitance discharges through a resistor, no? So then the output response will be an exponential, and which is about V out equals VDD e to the minus T over R on CL. So we know from our circuits classes that this would correspond to a tau equals R on CL. So then the high to low propagation time, that is between 50% of the input changing to 50% of the output, this becomes ln 0.5, which is about 0.69 R on CL. Okay? So, in general, no? So that's just the inverter. So in general, we have other gates, right? We have AND gates, we have OR gates. So for any gate in general, to implement any logic circuit that has one output, no? That is what is a gate is, no? So the PMOS pulls the output up and the NMOS pulls the output down, right? In a inverter. Now, in any CMOS gate, a purely PMOS network pulls the output up, a purely NMOS network pulls the output down to ground. And that's how we design these, no? So what is an example of that? So for example, we have this, no? So if we have NMOS transistors in series or parallel connection, we can do this. So for example, Y would be the same voltage as X approximately if A is high, no, and B is high, because these are NMOS. So then this would be low resistance paths, right? Now, on the other hand, if it was set up like this, then Y would be the same voltage as X if either A or B are on. Because if VDD, etong mga to, then you have a very small resistor between X and Y. No? Now, to complete the gates, then we can just apply ground here, right? So for example, if one of these were ground, then you're essentially saying that the output, no, or rather, let's put that in reverse. You're essentially saying that output Y is 0 if this condition is true. And that's what the NMOS pull-down network is supposed to do. So, this is now the concept of conduction complement. The PUN has to be a complement of the pull-down network. Okay? So, for example, here we have the NAND gate. Observe the behavior. If B is high and A is high, then Y is shorted to ground and Y is 0. Otherwise, if A is ground, no, then here, apologies, this should be PMOS, no? If A is ground, then this would be ground, just which turns on this PMOS, no? So then now, Y is shorted to VDD, and so on and so forth, no? So we can see here, no, that if this is, for example, let's go through all of these. If these are 0, no, then these are off. But if these are 0, then these are on, and now Y is connected to VDD, right? Next, if A is 0, then this is off, but this is on, so it's connected to VDD. If B is 0, then this is off, but this is on, so Y is connected to VDD. Okay? Lastly, if A and B are both 1, then these are both on and these are both off, so Y is connected to ground. Okay? Next, we have a NOR gate. So same thing happens. If A and B are both 0, then these are connected to VDD. So that's 1. If either of them are 1, what happens? Well, one of these would be closed, so we cannot be connected to VDD, and one of these would always be open if either of them are 1, so then Y would always be 0. No? And that's what a NOR gate is. No? An interesting observation would be that CMOS is always an inverting technology. So there's always NAND, NOR, or not. Okay? We can build more complex CMOS gates out of that basic principle. So for example, here, what does this gate do? So when you have a problem like this of analysis of a CMOS gate, you just have to look at one half of the network, no? Namely the pull-down network. So we'll see kung kailan 0 yung output. So the output is 0 if transistors with B and C inputs are parallel. So we have B or C. That's from here, right? Then that only happens if A is also on, right? Or actually, you don't have to take that path. It's 0 if D is on. So then, since this is when it's 0, we complement that. And this is the final logic expression for Y. No? So it is very quick. You don't even care about this. But when designing, it is important to get to get the pull-up network correctly. No? So in summary, we can use MOS transistors as switches, and CMOS is actually one of the best gates that we can implement. Okay?